Hi, in the second part of kinetic theory of gases, we're going to be deriving the kinetic theory equation. But first, we need to talk a little bit about the speeds of molecules in a gas. So, not all the particles in a gas will travel at the same speed. They will have a variety of speeds as shown on the graph here. So, some of the particles will have very low speeds, some will have very high speeds, and there'll be a peak in the middle at around the average speed. So, how could we quantify the speed of particles in the gas? So, to find the statistical mean, what you need to do is you need to add up the squares of each of the particles' speeds, all the way up to the speed of the nth particle. Capital N is the number of particles in the gas. You're then going to divide that by the number of particles in the gas, capital N, so you get the average of the square. You then square root the whole lot to get back to a speed, and that is called the RMS speed, root mean square speed. And it's a statistical method in order to work out the average speed for a distribution like this. It's worth noting that if the temperature increases, the distribution gets flatter. The peak will move further to the right of the graph as the average velocity will be higher, but it'll also get flatter because there's more particles that are at higher speed, so it'll look something like that. So the peak's less pronounced. Okay, so let's start deriving this equation. It's worth reminding you of the assumptions that we make in kinetic theory. We're assuming that the gases are point particles, so they have no volume. There are no intermolecular forces acting because remember the particles are very far apart. All the particles are continually moving in random motion. All the collisions are elastic, so there's no loss of kinetic energy. And finally, the duration of the collisions is much smaller than the time in between those collisions happening. Let's look at one particle within a container. Its speed can be split into x, y and z components, so let's call those u1, v1 and w1. So if we apply Pythagoras' theorem to that, the resultant speed squared is going to be u1 squared plus v1 squared plus w1 squared, and that's just applying Pythagoras' theorem in 3 dimensions. Let's say this particle now collides with a wall. So it's going to follow a path something like this in order to end up over here. And because it's an elastic collision and it's only collided sort of in the x direction, its component of velocity upwards isn't going to change, so that's still going to be w1. Also, as it's elastic, no kinetic energy is lost, so therefore its speed in the x direction must be the same magnitude as it was before, so it will just have changed direction, so this will be minus u1 here. Now we can work out the change in momentum for this collision, so delta P is going to be, it had minus mu1 as its momentum after the collision, and then if we take away its momentum before the collision, which will just be mu1, so we end up with a change of momentum of minus 2 lots of mu1. We're only considering the one direction, we'll deal with the other directions a little bit later on. In order to work out the average force that this collision is imparting on that wall, we now need to know the time it takes between collisions with that wall. So let's say that the distance here is Lx. The time between hitting this wall, okay, is going to be the distance travelled, which will be Lx that way and then Lx back, so it'll be 2Lx, divided by the speed in the x direction, which is u1. So if we write that down, our time between impacts, t, is going to be the distance travelled divided by the speed. So that's going to be 2 lots of Lx divided by u1. Okay, now we can apply that to work out the average force applied to that wall. The average force being the change of momentum divided by the time taken for that to happen. Now we want the average between impacts, so we're going to use the whole time between impacts. So that's going to be minus 2 lots of mu1, so that's the change of momentum, divided by that time that we've just worked out, so that'll be 2 lots of Lx divided by u1. That will give us m u1 squared divided by Lx. Okay, that u1 will end up here, that's why we've got the squared. So this u1 here will end up timesing that one up there, and these two 2's will cancel each other out. Now we can work out the pressure on that wall. So we need pressure equals force divided by the area. The area of this particular wall is going to be Ly times Lz. So that's going to be m1 u1 over Lx, because that was the force, divided by Ly times Lz, which will be m1 u1 divided by Lx Ly Lz. As Lx, Ly, Lz is equal to the volume, we can rewrite this as m u1 divided by the volume. We can now extend this idea to all the particles in the x direction. So we can work out the overall pressure in the x direction is going to be m u1 squared over v plus m u2 squared over v, and so on, all the way up to the nth particle, m un squared over v. So we can take the m and the v out at the front because that's in every single term. We then get u1 squared plus u2 squared plus, and so on, all the way up to un squared. This we can then take out and turn it into something similar to an RMS. So if we say that u with a little bar over the cross squared is going to be equal to u1 squared plus u2 squared plus all the way up to un squared divided by n. So that's the average squared speed in the x direction. We can use that to replace this bit in the pressure equation. So we end up with px is equal to m times n over v times u hat squared. You can apply the same logic to the other directions. So we end up with 3 terms. We end up with px is equal to n m u squared over v. Py is equal to n m v bar squared over v, and pz is equal to n m w bar squared over v. To work out the total pressure, we take the average of these 3. So the total pressure is going to be px plus py plus pz divided by 3. So let's expand that out. So P is going to be 1/3 of nm u bar squared over v plus nm v bar squared over v plus nm w bar squared over v. So that's going to be nm over 3v u bar squared plus v bar squared plus w bar squared. Now, this bit here is actually equal to the RMS speed squared. So we then end up with something that is very close to our equation. We end up with n m c RMS squared divided by 3v. So now if we take the v across to the left hand side of the equation, we end up with pv equals 1/3 n m c RMS squared, which is exactly what we set out to find.